Welcome once again to my YouTube channel. Today we'll be treating Taylor series method, also a typical example of ordinary differential equations. So remember, in our last videos we were able to treat Euler's method and Roncoulter. So today we'll be working with Taylor series, and here on my book written already are the steps necessary to follow when solving using the Taylor series method. So it says, taking h, which is our step size, to be equal to x minus x naught over n, which is the formula for calculating your step size. And we were told that we take at least the value of our step number to be 1, so that x1 is equal to x naught plus h, just as we have done under Euler and Roncoulter. So now, but the only difference between Taylor series and other ODE methods is that in Taylor series, the initial value problem, which is the function of x and y, the y, the x, we know it to be the what? A differential. So the y, the s, we can say is y prime, as you all know. So that's why I said the y, the s, which is the function of x and y, is y prime. Then when we differentiate y prime, we have what? Y prime prime. When we differentiate y prime prime, we have y prime prime prime, and so on. So that is just the difference between Taylor series and other ordinary differential equations method that we have earlier did. Okay, so and the formula guiding Taylor series is provided below for two-step number: first approximation and second approximation, and you can see the boundary conditions. So we have an example here. So we'll run through it very fast. It says that find by Taylor series method the value of y at x equals 0.1 and x equals 0.2 to 5 places of decimals from the equation dy dx equals to s squared y minus 1, given that y of 0 is equals to 1. So what do we need to do first? Like I do tell my students, first thing first, list out your parameters. You have to list out our parameters. So given in that question, we're given that our initial value problem, which is dy ds, is equals to what? S squared y minus 1. So let us call that what? Y prime, just as we've said in the note earlier. So
okay, what IVP means initial value problem?
Yeah, initial value problem given to us. Yeah, initial value problem. So also from that question, we remember that y of x naught is equals to y naught, just as we've been saying earlier. Y of x naught is equals to y naught. So from the question, we can say that x naught.
Sorry, sir, but this one is not here. This formula is not here.
It's something we have been learning constantly. So does not necessarily have. What I wrote here are just differentials, things that are different from what we have done differently from the other ones.
Okay, so you bring this formula to get x naught.
Yeah. So from here where we say y of 0 equals to 1.
Okay.
So x naught is replacing what? 0. So we can say x naught is 0, then y naught is 1.
Okay, which is this.
Then we have two value of x, which are going to write x to be 0.1, x to be what? 0.2. Right?
Sir, if I heard you well now, it's like this from the questions were given this. So from this, what is at the middle here represent the x naught that is here.
Yeah.
This y that this is present here, x naught, which is the one at the middle, which is 0. And that is how you got 0 here. And y naught is equals to 1. And that was how you got 1 here.
Yeah.
Okay, thank you very much.
Okay, so I haven't gotten that. Well, now we are going to find the value of h. Find the value of h.
Our step size.
This is our step size.
Okay.
Okay, and we say that h is equals to x minus x naught over n. So looking for h now, we know that the value of n is not given in that question. And from our note earlier, we say we take at least n to be 1, which is telling you that the number of steps required at least at the bare minimum should be 1. But knowing fully well that we are given two boundary conditions at x equals what? 0.1 and x equals to what? 0.2. That is to tell you that they expect us to find it under two assumptions. When x is 0.1 and x is 0.2. So that is to tell you that we have to assume that what? N is equal to 2. So if we assume that n is equals to 2, we can say our h will be equals to highest value of x is what? 0.2, right?
Okay.
Minus x naught is what? 0 over 2.
Okay, sir. I have a question. Why did, first of all, the first question is, why did he use the highest value of x? Because we have two value of x, 0.1 and 0.2. That's my first question. And the second question is that here we're told that n need to be at least 1. Then why did you use 2? Why can't you start from 1?
If we are to use 1, that means we have just one variable of x.
Okay.
In the question, we are given two values of x.
Okay.
So that is to tell you that if you look at this place, this first approximation, they said at x1 is equals to x naught plus h. So I would have said that you should take this as what? X1, and you take this as x2. But I want to break it down so that everybody can understand that at this point, if you are to use n to be 1, that means the value of x given to you is just 1.
Okay.
You are just to find it at one boundary condition, which is x1.
Okay.
But in this case now, we have two values of x.
Okay.
That's the reason why I said you assume n to be what? 2. So you are going to stop for the first one, and you're also going to stop for the second one.
Okay.
And now, knowing that fully well, if we say that we should use the lowest value of x here, assuming that n is equals to 2,
Yes.
we are going to be having 0.1 divided by 2.
Yes.
That means the value of h is going to be lesser. Looking at this now, 0.2 divided by 2 will give us what? Will give us what? 0.1, right? Which is equivalent to this.
Okay.
But if we say we use 0.1,
Okay.
let's assume this value is not given now.
Yes.
Then we can decide to say that our n is equals to 1.
Okay.
That time we can still get what? 0.1.
Okay.
So it's as easy, and depending on the nature of your question. If you are just given one boundary condition and you want to make your work very easy and light, you can just go with taking n to be at least 1. But in this question, you are given two boundary conditions, so we have to assume that our n is what? 2. If you are given three boundary conditions, that means you have to assume that your n is what? 3.
3.
And so on and so forth. And why you are dividing, if you are assuming n to be 3,
Yes.
the highest variable power of x is what you should use
Okay.
as your x. So take note of that.
This is the highest variable.
Yeah.
Okay.
So I haven't gotten h. Now we can now find x1 and x2. So looking for x1, remember that x1 is equals to x naught plus h. Then our x2 is equals to x naught plus 2h. So our x naught is what? 0. And our h now is 0.1, right? Which will give us 0.1. And our x naught is 0 plus 2 into 0.1, which will give us what? 0.2. So now, the next thing for
Okay,
us,
so what is the function of this x1 and x2 like this?
this is like I told you earlier, I would have said for the work to be very easy.
Okay.
From the question, I can say this is what? x1. This is what?
x2. Okay.
So, but following all protocols, like we know in engineering,
Okay.
that all protocols must be observed. That's what we did to justify that x1 is equals to 0.1 and x2 is equals to 0.2.
Okay.
So now having done that, we can now differentiate. Differentiating 1. And equation 1, y prime is equals to s square y minus 1, right? So if we differentiate y prime, we have y prime prime, right? Is it not?
Differentiating y prime.
So this is equation 1. So if you differentiate 1,
Okay, so okay, what you did there is that since we know that the y dx is the same thing as y,
y prime,
so
yes.
just instead of you writing the y dx, you
I
just
also
wrote
wrote
it as
y
y prime
prime.
equals to this.
Yes,
Okay,
exactly.
okay.
So now if you differentiate this now, what we are going to do, this is implicit differentiation.
Okay.
So we differentiate one, keep the other constant, differentiate the other, keep the other constant.
Okay.
So now let us differentiate with respect to x now.
Okay.
When you differentiate with respect to x,
that would be 2xy.
You are going to have 2xy plus, when you differentiate with respect to y, you keep the other constant, you have x squared y prime.
Yes.
Right?
Yes, because when we differentiate y with respect to y, we must put y prime at the
Yes,
back,
exactly.
which is the same thing as the y dx.
Yes, exactly.
This is just a simple implicit differentiation, that whenever you are differentiating y with respect to x, you keep y constant. So we differentiate this x, that will be 2x. So putting the constant joined, which will be 2xy plus, okay. Then if I differentiate with respect to y, because since it is y with respect to y, after differentiating it, I must put y prime, which is the same thing as the y dx. So if I differentiate, this x raised to power 2 will still remain the same, and this will give us 1. Putting the y prime at the back, which is this. Okay, I've gotten it. Thank you very much, sir.
So the next one is y prime prime prime, right?
Yes, sir.
So now let us differentiate this as well. With respect to x, what do we have? We have 2y, right?
This has already turned to 0.
Yes, this turns to 0.
Okay.
So with respect to y here, we have what? 2xy prime, right?
Okay. With respect to y here,
yeah,
that will be 2xy prime. Yes,
yeah,
yes,
2xy prime.
Okay.
Plus, when you differentiate this with respect to x, you have 2xy prime, right?
With respect to
x, with respect to y,
yes, no,
we are going to have x squared
y prime.
Okay. All right. So we can rewrite this by saying 2y plus 2xy prime plus 2xy prime will give us 4xy prime plus x squared y prime.
Okay.
So we can take this. Let us say since this is 1, this is 2, and this is 3. So let us go to the fourth one. Right?
Okay.
So when you differentiate 2y, you have what? 2y prime, right?
Okay.
When you differentiate with respect to x, what do you have? We have 4y prime, right?
Yes.
With respect to y, you have 4xy prime, right?
Yes.
With respect to x, you have 2xy prime, right?
Yes.
With respect to y, you have x squared y prime.
Okay.
Do you agree with me?
Yes, sir.
Okay. So we can rewrite this to be 2y prime plus 4y prime will give us 6y prime, right?
Okay.
Plus 4xy prime plus 2xy prime will give us what? 6xy prime, right?
Okay.
Plus what? X squared y prime. So I can call this equation 4. Are we moving?
Yes, sir.
Okay. Remember that the question says that to 5 places of decimal. Okay. Now let us look at our formula here. Our formula here says that y1 is equals to y naught plus h over 1 into y prime naught plus h squared over 2 factorial y prime plus h cube over 3 factorial y prime and so on, right?
Yes.
Now, if you are to count this, now this is the first decimal place. 1, 2, 3, 4.
Okay.
So to make it 5,
okay.
To make it 5, that means you have to look for y to the power of 4.
Okay.
So knowing that fully well, that what you just need to find is y to the power of 4, and that is what we have done here. So we don't need to progress.
Okay.
We don't need to progress. We know that y naught is the first one, y prime is the second one, y prime is the third one, y to the power of 3 is the fourth one, y to the power of 4 is the fifth one. So we can stop here since the question says that up to 5 places decimal.
Okay.
Do you get that? Do you have any questions so far?
I actually understand, but I don't know, for the sake of people that are view, maybe they may be confused of how we did this
The
part
differentiation?
and the implicit differentiation, the way we did it like this. I don't know whether they will be confused, or probably they will understand. But as for me, I understand it. So.
Okay. So moving on.
Maybe as you are watching, please, you can just let us know any part that you don't understand, any aspect that you don't understand. Please, you can drop it in the comments so we respond to you. Okay, so I'm listening. So I'm following.
Moving on. We first approximation is what we do next. First approximation. Taking x to be x naught and y to be y naught. Okay?
So may I ask, why, sir?
Just to justify whatever is here. To justify whatever is here. Why, wherever you see y, no is y naught. Wherever you see x, no is x naught. It's not a big deal. Okay? So applying a formula, initially we say y prime is equals to what? S square y minus 1, right?
Okay.
So we say s square y, x, we say to be x naught, right? So you are going to say you have what? X naught is what? 0 square, right?
Okay.
Y, what's y? 1, huh?
Okay.
Minus 1, right?
Okay.
So what would that give us?
That one will give us
0.
That will be
0
minus
1, right?
Yes, sir.
So y prime prime, we have it to be what?
2xy
Plus x square y prime, right? So substituting in values of x and y, 2 into 0 into 1, right?
Okay.
Plus 0 square. What's y prime?
Y prime
Is minus 1,
yes,
right?
minus 1, yes, sir.
So this should give us what?
This one will give us 0. This one will give us, I think it will be
Everything
0.
0, right?
Yes. So I don't know. Maybe at the end of this particular tutorial,
Okay.
maybe I can just explain to people that are watching how this part is being. You know, some people will understand it immediately. Why
Okay.
some might not?
No problem. So at the
Maybe
head of
some
the-
people that have forgotten implicit differentiations. Maybe I can just explain, or
No-
you, sir. Anyone, sir.
No problem.
Yes, sir. Thank you, sir.
Okay. So moving on, y prime prime prime, which has a value of 2y plus 4xy prime plus x square y prime prime. So it's going to give us 2 into 1, right?
Okay.
Plus 4 into 0 into y prime is what? Minus
Y
1,
prime
right?
is minus 1.
Plus
It's
2.
2.
Sorry. Plus 0 squared, right?
Yes, sir. And y prime is also the same thing as 0.
0.
So this should be 0. This should be 0. I think it will be 2.
2, right?
Yes, sir.
2. So y to the power of 4, which is 6y prime plus
6xy prime plus x raised to the power of 2 y prime prime.
So this one should give us
6 into 1
minus
1
plus 6 into 0 into
y
0,
prime,
right?
0, yes, sir.
Plus 0 squared, right?
Yes, sir. Y prime
2.
2. This should be 0. This should be 0. It should be minus 6.
Minus 6. So, having gotten all of this, you can now say, by Taylor series, we have all the necessary parameters, huh?
Okay.
So we just impute our formula now. We say y1 is now equals to, yes.
Okay.
y1 is equals to y naught, right?
Yes, sir.
Should I write the formula out first?
Yes, sir.
Y naught plus h over 1 into y prime naught plus h square over 2 factorial y prime naught cube over 3 factorial y prime naught h to the power 4 over 4 factorial, y to the power 4 not. So
add this one,
yes,
we have to stop
at
inside.
fifth decimal place.
1,
So
2, 3, 4, 5.
so knowing that fully well now, we have all the necessary parameters in our K. So let me divide this so as not to mix this together. Okay, so we can say our y1 now is equals to what's value of y naught? 1, right? Plus our h is 0.1, right?
Okay.
Over 1. Y, our y prime is what?
Look, y prime is -1.
-1, right?
Okay.
Plus our h square 0.1 squared over
2 factorial.
2 factorial is 2, right?
Yes, sir.
Our
Y
y prime is
0.
what? 0. Plus we have
0.1
0.1 to the power of 3 over 3 factorial is what? 6. That is 3 times 2 times 1, right?
Yes, sir.
Okay. Our y prime is what?
Is 2.
2 plus 0.1 to the power of 4 over 4 factorial is what?
That
4 times 3 times 2 times 1, that is 24. And our y to the power of 4 is what? Negative 6. So, moving further. Moving further, we can now say that our y1 is now equals to 1. I believe you can all see what I'm writing. 1 plus 0.1 divided by 1 will give us 0.1, right?
Okay.
Into -1, right?
Yes, sir.
Plus 0.1 squared will give us what?
0.01.
Okay, divided by 2.
That will give us 0.005.
So 0.1 square over 2 will give us what? 0.005, right?
Yes, sir.
Into what? Into 0. 0.1 cube divided by 6 will give us what?
0.1 cube divided by 6. That gives us 0.00167.
Multiply by 2, right? Then the last one, 0.1 to the power of 4 divided by 24.
Okay, 0.1 to the power of 4 divided by 24. So that gives us 0.0000417.
Multiply by -6. So could you please calculate all of this for me? After calculation, you should arrive at 0.9003. So y1 is equal to 0.9003 at x1 is equal to 0.1. Okay, so upon the check, we realized that the calculation for 0.1 to the power of 3 divided by 6 was meant to be 0.000167. That is 000. So please make sure you correct that in your book. So now we have the value of y1 to be 0.9003. It's very easy. What we just need to do next is our second approximation. Second approximation, which is very easy. We have to follow the same principle as well, where we taking our x to be x1 and our y to be y1, right? So we know that
Oh, sorry, sir, but we're told that x2 is equals to this.
we already have the value of x1 and x2. We've calculated x1 and x2 from this place. X1, x2. So it's not a problem. So x to be x1, y to be y1, just as we said in first approximation that x is s naught, y is y naught. So y prime, which is s square y minus 1, right? So remember that x1 is what? 0.1. y1 is what? 0.9003, right?
Okay.
So now x squared will be what? 0.1 squared, right?
Okay.
The y is 0.9003 minus 1. Using your calculator, you should get something like this, negative 0.9909. Please make sure you use your calculator to confirm all these values. Y prime prime, which is 2xy plus x squared y prime. And you please use your calculator to also confirm for me. Will give us 2 into 0.1 into 0.9003 plus 0.1 squared y prime, which is now negative 0.9909. So for this one, 0.18827.
It's correct.
So the third one, it says 2y plus 4xy prime plus x squared y prime prime. Here we are saying 2 into y, which is 0.9003 plus 4 into 0.1, y prime, which is negative 0.9909 plus s squared 0.1 squared y prime prime, which is 0.18827. And the answer we are supposed to have for that is after using our calculator, you should get 1.4061. 1.4061. Okay, and y to the power of 4. Y to the power of 4, which is our value is 6y prime plus 6xy prime prime plus x squared y prime prime prime. So here we are going to have 6 into negative 0.9909 plus 6 into 0.1 y prime prime, which is 0.18827 plus x squared 0.1 squared y prime prime prime, which is 1.4061, which our final answer is going to give us negative 5.8183.
Okay, thank you, sir. But I just want to confirm, sir, what is the difference between this? Because we use the same formula. I guess the difference is from here and here.
Yes, the difference is the value of x and y used.
So the first one we take anywhere we see y to be the value of our
Why
y
not? Yes.
So in this second aspect now, anywhere we see our y, we take it to be the value of our y1, which we got here.
Yes.
Here too, anywhere we see x to be x naught, but here now we take it to be x1.
Yes.
And our x1 was given to be 0.1. Where did we even got the 0.1? Okay, from here. Okay, thank you, sir.
Okay. So having calculated all of these, what we have to do next is to apply our Taylor series. So we say by Taylor series, we say our second approximation, y2 is equals to y1 plus h over 1 y.
This is the one you are writing, sir.
Yeah, exactly. Plus h squared over 2 factorial y prime prime plus h to the power of 3 over 3 factorial y prime 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 plus h to the power of 4 over 4 factorial y to the power of 5 4 1. Okay, so I haven't written that. Now we have our values. You can substitute in. Our y1 is 0.9003 plus our h still remains the same, 0.1 over 1 into y1, y prime is negative 0.9909 plus 0.1 squared over 2 into y prime prime is 0.18827 plus 0.1 to the power of 3 over 6. Y to the power of 3 is 1.4061 plus 0.1 to the power of 4 over 24, then negative 5.8183. So our value of y2, if you should input all of this in your calculator, should give you 0.8036 at x2 be equals to 0.2. So this is the value of our y2. So endeavor you cross check all of these values we have calculated and make sure that there is no calculator error. So here comes to the end of example 1 on Taylor series. Thank you and God bless you. Watch out for the next video.
Okay, so my boss asked me to explain this better for you guys. Now let me show you this for indicate. Maybe probably you have forgotten how to make use of an implicit differentiation to differentiate. So I will need to show you. So let me write my y prime. Let's write out our y prime. Our y prime equals to x raised to the power of 2 y minus 1. All right, you need to take note of something here. You need to take note of what? All right, so you need to take note of something here. I've written the value, I've written my y prime to be equals to this. Now, I want to explain to you how this differentiation comes in place for better understanding. So, now, what is y prime? Y prime is also the same thing as the y, the x. Yeah, I can also write it as dy over the x equals to y prime. That is, dy the x equals to what? Y prime. If I don't want to call it dy dx, I can call it y prime. You understand? So now you are asked to find you are given that our dy dx, that is our y prime, is equals to x raised to the power of 2 y minus 1. Now, if you are using implicit differentiation, we are using implicit here. Why is it implicit? You know, we have two different variables there. We have a variable of x, we have a variable of y. That is, we can say that y is a function of x, is also a function of y. Take note of that. It's both a function of x and as well a function of what? A function of y. So to differentiate now, if I'm to differentiate this with respect to this, I must apply implicit differentiation. You can also watch my YouTube channel on implicit differentiation. You understand? So now, if I want to differentiate this one for the second time, you know, if I don't want to call it, if I want to differentiate the y dx for the second time, I will call it the square y over the x square. Now, if I don't want to write it as the square y over the x square, I will call it y prime prime. Y prime prime simply means second derivative, that is second differentiation, which is exactly the same thing as this. So if I'm differentiating with respect to x now here, now you know that we have both x and y. So if I'm differentiating with respect to x, I will keep this y constant because I'm differentiating with respect to x. So if I differentiate with this x, whatever I have, I will then multiply it with this y. You know, this y is beside it. It's beside it. That is, multiply with it. So whatever I have, I will then multiply with this. So differentiating x raised to the power of 2, that will give me, using general method of differentiation, if you differentiate x raised to the power of 2, will give me what? 2x. So if I multiply this y with it now, it will give me 2xy. That is how you see, you arrive at 2xy here that you are seeing here. That is how it comes in place. Okay, so but now I'm not differentiating with respect to x alone. I'm also differentiating with respect to y, because we have both function of x and y here. So if I'm differentiating with respect to y now, I will have to keep this one constant, this x is power of 2. I will then differentiate this. Man, take note of something here. In differentiation, if I'm differentiating y with respect to y, you know, let's assume I keep this one constant now. You must put plus before you differentiate this. Plus, first of all, I differentiate with respect to x, keep this constant. I have this plus. I'm still differentiating this again. This time around, I'm differentiating with respect to y, keeping x is power of 2 constant. So, suppose I write the constant first. The constant is, the constant is x is power of 2. So, whenever I differentiate this, I will then multiply x is power of 2. Just as I've did here, I will multiply with the answer, okay? So, now, if I differentiate y, I'm differentiating y with respect to y. Just look at it. Imagine, y with respect to y. How does it sound? So, because of that, we say that whenever you are differentiating y with respect to y, whatever value you have, you must put the y dx at the back. Take note, whenever you are differentiating y with respect to y, maybe you have 2 as an answer, you must put 2 dy. After getting, let's assume the answer you get happens to be 2, you must put 2 dy over the x. And if I don't want to write it as the y over the x, I can write it as y prime, that is 2y prime. You understand? But now in this case now, our y, if I differentiate it with respect to y, mind you, this is constant now. I will multiply this with whatever I have. So if I differentiate this now, it will give me 1. Because if I differentiate x, it will give me what? 1. So if I differentiate y, it will give me 1. So 1 times x is power of 2, I will have x is power of 2. But mind you, since I am differentiating with respect to y, I said you write the y dx. And if I don't want to write it as the y dx, I will write it as what? Y prime. So that is how you see that we arrive at y prime here. This is given to be this, and this is given to be this. Please take note of this simple thing. Okay? Now, if I'm differentiating y prime now for the third time, now this case, now I'm not differentiating this because it will automatically give us 0. It is a constant number. So if I'm differentiating with this now, I'm differentiating with both x and y again. Now, starting from here, if I differentiate with respect to x now, I'll keep this one constant. So whatever I have, I will multiply with this. I will still differentiate this one again now, keeping this one constant, differentiating with respect to this. So first of all, let's start with x. So we have 2x. If I differentiate this 2x, or if you bring out 2 as constant self, I will have, if I'm differentiating with respect to x, let's do it in this form. If I'm differentiating with respect to x, I will have 2 and y as constant. You understand? I will have 2 and y as constant. 2 and y. So if I differentiate x, it will give me 1, right? So 1 times 2y will give me 2y. Okay? Now, plus, this time around now, I'm differentiating with respect to, I'm differentiating with respect to y now, keeping this, I'm differentiating with respect to y, keeping this 2x as constant now, this time around. So I will keep it as constant because whatever I have here, I will multiply with 2x. So if I differentiate y with respect to y now, we have just ordinary y here. So if I differentiate y, it will give me y. If I differentiate y, it will give me 1. But because I'm differentiating y with respect to y, it will give me what? It will give, after getting the answer, I must put y prime at the back. Okay? That is, what is the constant here? 2x. 2x multiplied by the derivative of y. If I differentiate y, will give me 1. 1 times 2x will give me 2x. But because I'm differentiating with respect to y, I must put y prime at the back. Now, coming to this part now. Plus, if I'm differentiating with respect to 2x, keeping this one constant. Now, if I differentiate with respect to this, keep this constant, I will have y prime to be constant. Okay? Then 2x, if I differentiate it with if I differentiate x raised to the power of 2, x raised to the power of 2, keeping this constant, I will have y prime. That is, the constant will be y prime, right? So if I differentiate x raised to the power of 2 will give me 2x. 2x times the constant before, the constant we have, which is y prime, plus, now I differentiate with respect to x here. I kept this constant. Now this time around, I'm going to keep this constant, differentiate with respect to this. So if I'm to keep this constant, I will have a constant of x raised to the power of 2. So if I differentiate with respect to y prime now, here we have y prime before. So it will change to y prime prime. The prime will now becomes what? Double. That is, it will become 2. So we have x raised to the power of 2, which is the constant, multiplied by the y prime, x raised to the power of 2, y prime prime. You understand? That is how we arrive at this. And we can still further simplify this to be, we can say 2y plus 2x. You can see that what is here and what is here are the same, so we can add them to say 4x y prime plus x raised to the power of 2 y prime prime. That is how we arrive at this, which is this. So if I say differentiate with respect to the fourth derivative now, if I'm differentiating with respect to this, the same thing applicable. Now this time around, if I differentiate with respect to y prime prime, what will it change to? The y prime prime will become 3. That is how that is how we arrive at 3 here. So the same approach applicable to the fourth one. If you find this helpful, please consider to like